In our next section, we're going to talk about the location separation independent protocol, which is LISP. Specifically, what we're going to be using for in our particular use case is essentially an overlay VPN, similar to what we would do with like a DMVPN or a GRE tunnel, where we're hopping traffic over the service provider core in the middle, as opposed to our previous examples of like a layer 3 VPN where we're routing with the provider in the middle. LISP is going to be an overlay tunnel that's basically transparent to the infrastructure that's in the middle of the network. Now, LISP itself is a pretty big topic. So what I'm going to be doing in this section is basically just talking about some of the basics of what is the protocol, what it is designed to do, and then we'll take a look at some config examples that are going to be within our scope. But in general, what LISP is just another tunneling protocol. Tunneling protocol like GRE, like OTV, L2 VPN, L3 VPN, etc. It's an IP in UDP tunnel specifically. Now, what the goal of the tunnel is, though, is a little bit different than the other ones, that it's trying to separate what is the address of the endpoint, like your application server, and the location of where that endpoint is currently exists, like what is the router's link to the service provider. Now, it is a standards-based protocol. RFC 6830 is where it's defined, so if you want to get the nitty-gritty details about the packet format and stuff, you can take a look at that afterwards. But in terms of the overall use cases of why we would want to use this, there's going to be three main ones that are going to be for our use case. One is going to be for load sharing ingress traffic as we're receiving packets in from the service provider or service providers. One is going to be for IPv6 transition, that we could tunnel IPv6 over the IPv4 core. And then the other one is for VPN service that's going to be similar to MPLS Layer 3 VPN, that we could separate the network into multiple logical routing tables based on VRFs, and then we can encode that the routing table information into the data plane of the tunnel to separate one customer's traffic or one like department's traffic for another. The other kind of big buzzword that goes along with LISP is VM mobility, which would be for your data center interconnects. Like if you do VMware vMotion from one data center to another, and then you want to make sure that the ingress traffic is routed correctly to that VM, that's going to be the other big use case. But we're going to be looking at the first three here, basically just the first two, I should say, that we'll look at in our examples. And then if you go to Cisco's main LISP site, which is just lisp.cisco.com, you can see some other information about what are the other particular applications about LISP. Okay, so before we get into the implementation, we do need to talk about the terminology, because like any of these new protocols, if you don't understand what the different acronyms mean and what their roles are in the network topology, then it's going to be pretty tough to figure out what are you trying to do to begin with. Okay, so the first most important two that we have are called the endpoint ID and the routing locator, or the EID and the RLOC. Now, the EID is going to be analogous to the server's endpoint address, like your web server has IP address 1234. The routing locator is going to be the router's IP address that would be used as the ingress or egress link in order to reach that particular service. Okay, so let's say, for example, that you have your web server here somewhere in the data center, and then you have your layer 2, layer 3 network in the middle. Okay, it doesn't really matter the details about this. And then you get to whatever your WAN edge router is. Okay, like we have router 1 that's going up to ISP A. Maybe we have router 2 that's going up to ISP B. So the endpoint identifier then is going to be talking about the IP address that is directly assigned to the web server, whether it's an IPv4 or an IPv6 address. The routing locator is going to be the interface address that router 1 is using to reach the ISP A, or that router 2 is using to reach the ISP B. Now, the goal of this protocol is to provide a mapping between the two of these to say that if you want to reach this particular endpoint, you need to route your traffic to one of these routing locators. You either need to route the traffic to router 1, or you need to route the traffic to router 2 inside of the tunnel. Then those routers will decapsulate the tunnel and then natively forward the traffic to the destination. And again, we'll see the reason why you might want to do that. Could be for ingress load sharing, where we want to do like a 50-50 share between these two different ISPs, or that maybe the web server is IPv6 native, but the transport network is IPv4 only, or we're trying to do service separation like a layer 3 VPN. Now, in order to associate the two of these together, we then have what we call the mapping database, or the MDB. Okay, mapping database is going to be how we associate the endpoint ID to the routing locator. And in the control plane of LISP, this is going to be the most important portion of the protocol. You could think of this as loosely analogous to DNS. That if I go to cisco.com, I need to ask the DNS server what's the mapping between the domain name, cisco.com, and then the mapping to the IP address. In the case of LISP, we're asking the map database or the map server specifically, what is the resolution between the endpoint that I'm trying to reach and then where it's actually located in the network. Do I reach it through router 1's interface? Do I reach it through router 2's interface, etc. Now, in order to do this then, in the control plane, we need to have the device that is holding the database. This is called the map server. Okay, so map server knows about what are all the associations between the endpoints and the routing locators. We then have the map resolver that is going to tell people what is the resolution between the two of these. In most typical cases, you have both of these combined, that the map server and the map resolver is going to be the same physical box, but technically it could be separate boxes in the case you're trying to do some sort of hierarchy or some sort of redundancy design, where you can have multiples that are separate physical rows. Okay, then we're going to have the boxes that are asking the map server and the map resolver, how do we actually reach the destinations? So these are called the ingress tunnel router and the egress tunnel router, but are more commonly combined together in what we simply call the XTR. Now, specifically what these boxes are doing are first and foremost doing a resolution between the endpoint ID and the routing locator, which again, endpoint ID is going to be your host address, and then the routing locator is going to be the router's interface that is facing towards the upstream WAN. It's like your point-to-point /30 or 31 link that's going to the ISP. Now, specifically, what these roles are doing is the ingress tunnel router is asking the map resolver, which is the MR, asking it for what's the resolution between the endpoint and the routing locator. Once we figure this out, we're going to take our IP packet and then we're going to put it inside of LISP, which specifically is a UDP and CAP. Okay, when it gets to the other side, it's received by the egress tunnel router. So ingress and egress, we're talking about this from the perspective of the WAN cloud in the middle. So it's ingressing into the service provider network, then it's egressing out of the service provider network back to the site that's running LISP. They're going to be receiving the traffic that is encapsulated in UDP. We take out the IP packet in the middle and we forward it towards the destination. The egress tunnel router is also the one that's telling the map server what is the resolution between my endpoint ID, which again is like my server, and then the routing locator, which is going to be the router's IP address. But again, in the vast majority of cases, you do both of these at the same time, that you consider to be an XTR, both an ingress and egress tunnel router at the same time. Okay, once we get through the basic functionality, then we'll talk about what is the use case for the proxy ingress or proxy egress routers. This is going to be when we have a LISP site that we want to talk to the non-LISP aware network. So the practical use case for this would be that you have your own internal private WAN that you're creating by using LISP, but then your sites want to route to the internet doesn't natively run LISP. So you need some sort of box that's going to translate between the two of them. That's what this proxy router is going to be. So it's the same type of logic as the ingress tunnel router or the egress tunnel router, but it's proxying for the non-LISP sites, and then typically you would combine these together, which is considered to be the PXTR, both the proxy ingress and proxy egress at the same time. Okay, so there's a question here. So the RLOC becomes the global address that is used to peer with the ISP. Yes. Okay, the key point about all of this magic that LISP is doing is that the routing locator has to be a globally routable address in the global unicast table. So as we compare that to like our L3 VPN design, in L3 VPN, the globally routable addresses would be the PE core addresses. So the service provider doesn't need to know the details that's going on inside the inside the customer network, because those are the endpoint IDs, but the service provider does need to be able to route to the routing locators, which is essentially the infrastructure links of the routers. Now, what we'll see in our particular use case here, if we take a look at our diagram, we're going to have two different sites that are connected by LISP. We're going to have site number 1 that's over here on router 4 and router 5, and then site number 2 that's over here, router 3 to router 7. Okay, the ultimate goal is that we want to get connectivity between the loopback of 6 and 7, and then we're transporting this over the provider network in the provider core. And then later we'll say that these other networks over here, this is going to be like the internet. Now, in order to accomplish this connectivity to begin with, again, we need to make sure that the core of the network has IP reachability to the routing locators. Routing locators, in our case, would be considered the interface addresses that are between, and just a second here. Our routing locators would be the interface addresses that are going from 5 to 1. So this is an RLOC, this is an RLOC. Then between 3 and 2, and 3 and XR3. And then the endpoint ID is going to be the internal address that we're trying to tunnel towards. Now, somewhere in the middle of the network, we need the box to resolve the two together, so kind of like the DNS server. That again is called the map server and the map resolver. In our case here, we're going to say that router 8 is both the map server and the map resolver. And then the devices that are actually running LISP are going to be routers 3, 4, and 5. So these are going to be the XTRs, which are the ingress tunnel routers and the egress tunnel routers. So these are doing the actual LISP and CAP. And in order to do this, they need to talk to the map server and the map resolver. So what this means from an IP connectivity point of view to begin with is that routers 3, 4, and 5 need to be able to ping router 8. Same as like DNS. If I don't have IP reachability to the DNS server, then I'm not going to be able to actually do a resolution for whatever names that I want to reach. Now, in terms of the initial configs here, basically what's going on is that the core of the network is set up for regular IGP routing. So if we look at like on, let's say XR1, and we look at the just show IP route, we have ISIS running in the core, and specifically this is getting us reachability to what our map server is going to be, which is router 8. And then it's also getting us access to our routing locators. Routing locators specifically here being the link between XR1 and router 4, the link from router 1 to router 5, which is this address here, and then the one from router 3 to 2 and 3 to XR3, which would be 10 to 3, and then 10, 3, 13. So we have to be running some sort of routing in the core to begin with in order to establish the infrastructure reachability. But the key point here is that the devices in the core, we are not going to have reachability to 6666 and to 7777. So same as like in L3 VPN, the core of the network doesn't need to know the details about what's the source and destination. They just need to know the details about the ingress and the egress through the core of the network, which specifically is the routing locators of the XTRs, the ingress tunnel routers and the egress tunnel routers. Okay, also again from the map server, which in this case we're going to configure it as router 8, we need to be able to get reachability to these routing locators. So I'm going to ping to 10.4.11.4. And the source is loopback 0. Okay, same is on router 5. So router 5 is 10.1.5.5. And then we have 10.3, 10.2.3.3, which we do. And then 10.3.13.3, source is loopback 0. Okay, so we have reachability. There's a question here, does XR do LISP? Yes, it does. So you can run it as the map server or you can run it as the map resolver. The syntax is basically the same between them. The version that I'm running seems kind of finicky with XRV, that it doesn't really seem to support the data plane. I'm not 100% sure if the newer version, which is 5.3, will fix this problem. But you'll see some examples in the workbook that are also based on XR. If you just basically copy and paste it in, the control plane forms, but it gets some sort of memory allocation error when it goes to forward the data plane. So for the completeness of the example, to actually show the encapsulation being created, I'm going to be showing it just on iOS, but you'll see the syntax is basically identical between the two of them. So I would assume within the scope of the lab exam, if they're testing on XR, they're just using a version that supports it fine in the data plane. Okay, so next what we're going to do is to configure router 8 to listen for these registration messages that are going to be coming in from the other boxes. Okay, so let me show you guys where this is located in the documentation. And we basically want to look at the minimum config to start, and then we'll start to go beyond to other variations, see what the customization is. So let's go over to the iOS XE documentation, and it's got its own section under routing. So under configuration guides, it's under IP routing for LISP. Okay, we want just configuring LISP. So if you've never heard of the protocol before, make sure you start with this section. Just read the basic overview before you start to get into the specific config syntaxes. Okay, what we want to do is to configure a private LISP mapping system using a standalone map resolver or a map server. Okay, now configuring a public mapping system, this would basically be if you're buying LISP service from your provider as a customer. And typically, the real use case for that is going to be for ingress load balancing of the links, which I'll talk about that a little bit later, why you would want to do that in a real design. But in our case, we're basically building this as if it's a private network. Okay, so we're configuring standalone map server, map resolver. Okay, so we go to router LISP. We specify that this guy is going to be a map server, this guy is going to be a map resolver, and then we specify what sites are allowed to register to us. Now, the basic logic of this is like who is authoritative for the domain. So I can't go in and edit the root DNS server for Cisco.com because I'm not authoritative for that particular domain. Same basic logic here is that you need some sort of level of security to say, I need to make sure someone else is not registering my address space. So the map server is the one that is enforcing this. It's basically saying, I need to know what is going to be the endpoint ID, or basically what is the server's IP, or more specifically the server's IP subnet. And then who can register it to me, that we're just going to use a password for authentication. So this is using a hash behind the scenes. Okay, in our particular case, we're going to start with router 8 talking to router 5, where router 5 is going to be registering the endpoint of router 6, so let's say 6666/32, and then also the directly connected link between them, which in this case is 10.5.60/24. So we'll see that there is a lot of manual config that's related to this. You can't just dynamically register whatever addresses you want. It has to match between the XTR and the map server map resolver. Okay, so on router 8, let's go ahead and start the map server config. So we say globally, router LISP. We're going to be an IPv4 map server and a map resolver. Okay, we'll see a little bit later that we can also do this with IPv6, and they're mutually exclusive between each other. They're unrelated to each other in terms of config. So we're doing both at the same time. We're the IPv4 map server, and we're the map resolver. Okay, basically every single IP address on the box is now listening for it. We're going to use the loopback of it, but you could use any interface address. It's basically listening on every single link. Okay, then we're going to specify what are the different sites that are going to be registering with us. So we give it a name. Let's say that this is going to be router 5. And we specify what are the prefixes that they're allowed to register to us. So the prefix in this case is going to be 6666/32. And we'll also say that it is 10.5.60/24. Now, as part of this registration process, you can also say, do I want to allow them to accept more specific prefixes? So let's say that the customer has a /22 allocation. You could say, well, I'll accept /24s or 25s to them because they're subnetting it down further. So you don't need to match every single address. It could be as part of an aggregate. But in this particular case, I'm just saying these prefixes exactly. So those are the exact routes that they're going to advertise to us. Okay, then we need to give it a password. So authentication key, we'll say router 5 password. Okay, so same thing is going to be when we're getting the registrations coming in from router 3. So router 3 is going to be registering 7777/32. And then this link between them here is 10.3.70/24. I'm going to say that the map server is going to allow more specific prefixes of this. So let's say that it's just 10.3/16. So as long as it's anything under that aggregate, then the map server is going to accept the registration. Okay, so we configure another site. We'll say the site is router 3. EID prefix, again, the endpoint identifier is going to be 7777/32 and 10.3.00/16. But I'm going to, again, accept more specific prefixes. Okay, you could also put a tag into it. You'll see there's a lot of customization for the protocol, but at least for the minimum config, there's really not that much that we need to do. Okay, so let's say show run section LISP. And this is basically going to be our minimum config for the map server. Okay, so next we're going to go to the boxes that are actually doing the tunneling, which are router 5 and router 3. And we need to do the registration of our prefixes to the map server and to the map resolver. Okay, before we do this, I'm going to turn some debugs on router 8 so we can see specifically what's going on in the control plane. We're going to debug LISP, and we're going to debug the control plane, basically just everything. Okay, debug control plane all. Specifically, what we're going to be looking at is going to be the map server registrations and then the map server requests. Okay, the request and the notify. Notify is going to be the responses back to them. But in this case, basically just everything. Okay, so next on router 5, we're going to configure globally router LISP. And in the case of the documentation, this is where we would be configuring either the ingress tunnel router or the egress tunnel router, which is they're calling the XTR. Okay, so they're saying there's a couple different variations. Maybe you're dual homed, you have 2 routing locators, and you have an endpoint identifier. This would be where you have 2 service providers, and you're saying I have linked to service provider A, I have linked to service provider B, but both of those can be used to reach my servers that are behind me. So I want you to keep a mapping of what the endpoint ID is to these routing locators. Routing locators, again, normally being the point-to-point links to the ISPs. The endpoint ID, this is where your actual application is. Okay, specifically what we do is to do a database mapping. Database mapping is going to say the endpoint ID, in our case this is going to be like 6666/32, and then it maps to an interface locator, which is going to be 10.1.5.5. So what this is basically telling the other LISP sites, if you want to reach router 6, tunnel traffic to 5. 5 already has a route to 6 internally, but the devices in the transit path don't have a route to 6. Okay, this is assuming then from the infrastructure routing point of view, that if we look at router 5 and do a show IP route, we already have some internal routing that is getting us reachability there. Where specifically in this case, what I have set up is that router 5 has simply a default route that's pointing towards the provider, and then we're running EIGRP internally. Okay, EIGRP is advertising that default route over to router 6. Okay, so on router 5, we went under router LISP, and we're going to do a database mapping. Okay, database mapping is what's making us the egress tunnel router. Okay, so we're going to register that information with the mapping server. The endpoint identifier in our case is 6666/32. And then what does it resolve to? Okay, it's going to resolve to the address 10.1.5.5. We then need to set a priority value, and we set a waiting value. The priority value determines are we going to use this or not. So if one box is a priority of 1, the other box is a priority of 2, we're only going to tunnel traffic to the box that has the priority of 1, the lower value. If the priorities are equal, so if we say the priority is, let's say, 100, and it tells you right there, lower takes preference. If the priorities are equal, we're then going to weight the traffic between the locators. This is for the purpose of load balancing. And you'll see that this is a really interesting function of the protocol, that you can use this for ingress traffic engineering, which is very difficult, as we saw when you're doing stuff like BGP, path manipulation. You always have control of how traffic is leaving the AS, but it's fairly difficult to influence the return traffic equally. So you could do something like AS path prepending or MED, but you can never really get it to do like a 50-50 load sharing based on the flow information or based on the bandwidth of your links. So let's say, for example, that I have a 1 gig Ethernet, plus I have like a backup ATM OC3, and I want to load balance these in a ratio of 1,000 to 155, so basically 1,000 megabits per second to 155 megs, or basically like a 10 to 1 ratio, give or take. So it would be like a 20 to 3 or so. And with Lisp, you can do this really easily just by setting what the weighting is. Okay, so if we set that this guy to 10 and we set the other guy to 1, it means that it's going to distribute 10 flows that way for every 1 flow that we're going the other direction. Okay, but for now, since we only have 1 address, the weighting doesn't matter. We'll just say the weighting is half of the default. Okay, half of the possible value. We'll say 50.